Okay, so this is problem 13.4, C8H11N. Just inspecting our carbon NMR, we have three peaks above at lower field than 100, 117.7 as a singlet, 126.3 as a doublet, and 127.1 as a singlet. We have tables of data here, so when we start seeing things in this region, we start thinking about alkenes. And so just inspecting, we have some examples of alkene chemical shifts. Also included some well, we also have this in this table we've plopped in some nitrile compounds. Remember that nitriles also come in this region. We have a nitrogen and several points of unsaturation to contend with. Okay, so but that's getting ahead of ourselves. Let's remember our IHD calculation. Our IHD is going to be 4 for this compound. If we do our H on C analysis, we see that all 11 of our hydrogens are on the carbon atom, so we do not have any NH bonds. We look for symmetry in this compound and don't find it. Okay, so all of our carbons are unique. Okay, so remember we were thinking about alkenes. You might be tempted to think of ways to use all of these carbons, 127, 126, and 117, in an alkene. Really, the only way to do that would be by using an alenic type structure, similar to that one shown here. If you look at your tables, you pretty much show that this is way off base. We would be expecting for an alene to have that central quaternary carbon at 213 ppm. We have nothing close to that in the carbon NMR, so that's not the right solution. So we have a nitrile here, and then we have an alkene. Okay, so the nitrile takes care of 2 IHD units. Remember that, and the alkene will take care of another one. All right, so with the nitrile, then, and just going back up, we remember that we have for a nitrile chemical shift of about 119. We see a peak at about 118, which is a singlet, which is consistent with that. We also would expect for a nitrile at the alpha carbon, we would have a chemical shift relatively downfield, 2.3 in this example. We see peaks that are shifted downfield, especially this peak with 2 hydrogens at 2.97 ppm. So we're going to keep that in mind as we go forward. Okay, so the nitrile and the alkene take care of 2 of our IHD units. Then that means that we also have a ring that we're going to be thinking about down the line. Okay, so all right, so if we go and look at our structure then, so we have a doublet and a singlet. Okay, I have these drawn backwards. This should be the singlet, and this should be the doublet over here, but we have a doublet and a singlet for the alkene. All right, we have a hydrogen attached to one piece of this alkene, and then we have a nitrile functional group. We've deduced from our carbon from our proton NMR that this peak at 2.97, as I mentioned before, is going to be a singlet that is alpha to the nitrile. The virtue of the fact that this is a singlet tells us that we have a fully substituted carbon that is found next door. All right, so with that, we know that we have a methylene. We have a tri-substituted alkene with a single hydrogen attached to it. We see when we go to this hydrogen, we see that it comes with a chemical shift of 5.79 ppm, and it appears as a triplet with a coupling constant of 6.2 hertz. So what does that tell us? That tells us that our alkene is appearing as a triplet, which has a 6.2 hertz coupling constant. Okay, so then with that, we know that we have a methylene next door. And so we have now a few fragments. We have our nitrile fragment, We know that we have a ring, we have an alkene fragment. If we just fill in the blanks, we have a bunch of triplets that are left. There's no other methyl groups on this molecule, and then just 8 methylenes to, eight more hydrogens to put in as 4 methylenes. We complete the structure. Shown here at the bottom is a nitrile with a methylene attached to a cyclohexene ring.